Hello and welcome to PyData Global 2021. My name is Natalie and I'm very happy to be here and to be your host for this session. Please, if you feel comfortable in doing so, please rename yourself to the name you would like to be called by in this session. Would be lovely if you could also add your pronouns in here. And if by any chance I pronounce your name incorrectly, please correct me at any time. Please also note that we are recording this session. I would like now to welcome Anders Berkeman, Drougge, and Sofia Hörberg to our session, and they will talk about computations as assets, a new approach to reproducibility and transparency. Dr. Berkeman has been working with data science and data processing architectures for the last 10 years. He is a master researcher at Ericsson Research and a frequent teacher in machine learning and data science at Ericsson. Carl is a senior software developer with a wide experience including high-level Python programming, as well as design of efficient low-level libraries in C or assembler. He is a researcher at Ericsson Research. Sofia is a data scientist with years of experience, and she's part of Combined AB Group. And with that, I give the floor to the speakers. Thank you for joining us today.
Thank you. So hello, my name is Anders Berkeman, and I represent the talk Computations as Assets, a new approach to reproducibility and transparency by Sofia Hörberg, Drougge, and myself. This talk is based on the open source project ExAx. ExAx is a Python library for parallel processing and streaming of large datasets. ExAx stores computations on disk so that it is easy to retrieve them when needed. Things are computed only once, computations are reused instead of recomputed. The ExAx project was initiated almost 10 years ago at Swedish AI startup ExpertMaker. It has been used in projects with customers such as Safeway, Vodafone, and eBay, to name a few. It has been used for data analysis and data engineering tasks, but also as backend in recommender systems, producing live recommendations for US customers. In 2016, ExpertMaker was acquired by eBay to help advancing their structured data initiative. And in 2018, ExAx was open sourced by eBay under the name The Accelerator. Since then, more than 1,300 peer-reviewed commits have been added to the project. If we summarize the design goals in 2 bullets, it is first to minimize risk for manual mistakes. This is achieved by letting the computer do bookkeeping of inputs, outputs, results, and so on. And as we will see, this leads to an automated, transparent, and reproducible workflow that can be taken directly into production. And second, to maximize efficiency. Critical parts are written in the C programming language. Results are reused and not recomputed where possible. Processing is making use of all cores in the machine. And with a small footprint, it can be installed on Raspberry Pis, laptops, as well as rack servers. Let's start with an example, the Backblaze dataset. Backblaze is a company in the data backup business. They have more than 100,000 drives spinning currently in their data centers. Every day, they collect a set of more than 100 parameters from each drive, and this data is then shared openly on their web page. In total, the complete database contains almost 250,000 drives of 135 different models collected daily since 2013. A number of data science and machine learning projects have been based on parts of this data. In our example, we have generated a video visualizing all 250 million rows in this data set. The video that we will show is rendered in full HD resolution and runs at a frame rate of 60 Hz. All source code for this animation is available on our GitHub page, and we will present a link at the end of this talk. A frame is composed of approximately 2 million pixels, and there are 250,000 drives, so if we let each drive be represented by 4 pixels, we can actually squeeze in a visualization with all drives on screen simultaneously. Then we render 1 frame for every day in the data center. In this first frame, we see a number of light gray rectangles that each represent a number of drives of a particular model. For example, this rectangle here corresponds to a number of Hitachi drives. There are 60 drives per row, because this is the number of drives that fits into a Backblaze drive pod. So this rectangle corresponds to maybe 60 by 80 or 500 drives. Over time, some drives will be removed and some will fail. We have marked the removed drives with black, and failed drives are represented by an animated circle. I'll start the animation now. The flashing bright areas represent new drive being added to the data center. Somewhere around 2015, Backblaze starts adding 1,200 drives at a time, and we can see it happen here and also here. On my screen, this animation runs very smooth, running at 60 frames per second. I guess the experience in the other end of the Zoom channel is not that smooth, but the video will be available afterwards on YouTube. Note that we are visually exaggerating the failures. Approximately 1% of the drives fail every year, and Backblaze have a very strong redundant storage method that has been proven to work extremely well. Now, let's go back and see how this was actually done. We start with the very basics. Imagine that we want to execute a program. Input to the execution is source code and parameters, such as location of input data. And output could be some kind of graph, table, animation, just something printed to standard out. This image illustrates this very simple situation with the actual program execution consuming time and energy in the center. Now, what we do is that for every program we execute, we create a new empty directory in which we collect and store all input and all output associated with the execution. In addition, we also store meta information about the execution itself, such as, for example, which Python interpreter that was used and the program's execution time. So to be specific, we store source code, input parameters, as well as all output files and printouts together in a new dedicated directory. In this presentation, we've drawn these directories that we call job directories in the shape of a chest. Now that we have stored everything, we realize that we can query all existing job directories to see if the program that we want to execute have already been executed before. If it has been executed before, we can immediately return a link to the existing job directory. There is no need to execute anything. On the other hand, if we are seeing something that we have not seen before, we need to execute it. And when we do, we create a new job directory and store everything related to the execution inside it. Then we return a link to this new job directory. As we will show you next, this idea leads to a number of advantages, such as being able to do faster design iteration. But the advantage we will talk about first comes from the perhaps a bit surprising observation that we do not need to name or bookkeep intermediate files anymore. The way it works is by using what is called build scripts, and you can see an example here that builds 3 jobs. The key idea is that you can use existing jobs as input to a new job, thereby creating dependencies between jobs. For example, job number 2 here, the pre-processing job, uses job number 1 as its input. The job directory associated with job 1 contains the data needed by job 2. The result of the complete execution is linked to the jobs creating them using soft links, making it transparent from which job the results were computed. On a low level, here is what it might look like. Imagine we have 2 programs that we run in a sequence, one before the other, and that the first is passing data to the second using an intermediate file. To the left, we see what we might call the traditional way of doing this. We execute one program after the other. The first program writes, for example, a pickle file, and the second program reads the same pickle file back. For this to work, we need to make sure that the file name is the same for both programs. To the right, we see the ExAx approach. It uses a build script in Python, and as you can see, there is less code and no explicit file name. The first job just returns the intermediate data upon completion. And the second program reads this data from the source job that was assigned using an input parameter. Internally, a file is created by the return statement, but its name is of no relevance to us. During development, every time we make changes and re-execute the build script, new jobs that correspond to these changes will be built and stored on disk, unless they already exist. This opens up for faster and easier experimentation and trying out what-if cases. We can always go back to a previous state by just undoing changes in our text editor and rerunning the build script, which will make all outputs up to date immediately. Another thing we can do, for example, is to work on 2 or more Git branches simultaneously. Every time we switch branch and run the build script, all updates will be updated, all outputs will be updated accordingly. And this is the key idea. Using ExAx, we will not fetch the wrong files or consider results that are not up to date. This minimizes risk of manual errors. And the main reason for this is because intermediate files are fetched not by name, but by function. If we want a particular file, we call the function that generates it instead of using an arbitrary file name. Also, running a build script ensures that the output will correspond to the source code and the input data. No need to rerun everything from scratch just to make sure. Let's spend a few minutes talking about what we mean when we say transparency and reproducibility. We start with transparency. This image illustrates that the result, in this case, a graph, may depend on many source files and many input files. Looking at this result, this graph, how do we know which files and versions that was actually used to create it? We want to be able to observe all data and all source code associated with any result in order to answer questions like, did we include the last update of the input data? Or was this generated with or without the patch that we did yesterday? And so on. Using ExAx, it is straightforward to view the source code of any built job, follow the dependencies back to other jobs all the way back to the input data. And we can do this on the command line or using a web browser. And in the web view, we can also view tabular data, images, video files, etc. It's very convenient. Reproducibility then. Reproducibility relates to a number of things such as fixed seeds for random number generators and stable sorting. In this context, it means that we should be able to reproduce a result given a complex scenario involving multiple versions of source code and data. Assume that we have tried different versions of the code, but we always use the same intermediate file names. This is only reproducible if we know which version that was run last. Using ExAx, all versions will be available and the result will correspond to the current or active version. And here is another scenario. Let's assume that we always create new files. Question is then, which of these outputs corresponds to which versions of all these source files? Again, using ExAx, all versions are available, and running the build script will ensure that the output corresponds to the current state. Let's now move back to the Backblaze example. A program of this size is typically not implemented using a single program. Instead, we rely on divide and conquer and separate the project into a set of programs that each solve one part of the total problem. The main tasks in this data to video product are importing and typing all the CSV files, do the required amending to get the dataset in perfect shape, render all the video frames, and then encode all these frames into a single video file. This project has 2 main phases, where the first is to import, type, and amend the data, the preparation phase. And the second phase is the creative part, where we use the imported data to create the frames in the video file. This image illustrates most intermediate files in the project. Input data enter at the top left, moves right and then down and then right again until we reach the output video file. In between, we can see the different jobs and how many files they create internally. For example, the frame rendering job needs 1 + 1 + 7 input files to draw all the frames. These files in turn are generated from the imported and typed data that is stored as hundreds of thousands of files. Out from the rendering job, we have more than 2,800 files, one for each frame in the movie, which are then video encoded by FFmpeg into one output file. Now, why do we see hundreds of thousands of files in the CSV import jobs? We will get back to that, but basically it is because we have 3,000 CSV input files times 150 columns, and we want to be able to read the columns independently for speed reasons. And in practice, these numbers are multiplied by n, where n is the number of CPUs in the machine, to take full advantage of the parallel processing hardware in a modern computer. Nevertheless, these files are never visible to the user. We mention them here for reference, but we really don't need to know this in order to write the program. This table shows the execution times for the different parts of the project. It also shows how many iterations we did to complete the movie. Importing takes most of the time, more than half an hour, and it creates approximately 3,000 jobs. And this is run only once. Amending the dataset takes a few iterations to get right, but it takes only 6 seconds per iteration. Then we need to collect the data to render, and we do this using 3 different jobs that executes in 44 seconds. And it took 19 attempts to get that one right. Most of the development effort is then spent in the rendering code. Here we need to try out what looks good and what does not. By looking in our work directory, we could see that we ran this job more than 100 times. And in order to watch the video, we also need to encode the frames into a video file. Encoding all frames takes 17 seconds, since FFmpeg can only use a few CPUs. So we added a parameter that by default only generates 2 seconds of video. Then we're down to 1 second. So the total iteration time from changing the source code to having a new video to watch is only 7 seconds. As we all know, fast iteration is fundamental for the creative process. Being able to try out ideas in only a few seconds is a game changer. You may argue that this is fast because we are using a fast computer. So we also ran this on a laptop from 2018. Import then took 45 minutes, and the design iteration was less than 50 seconds. So this is still okay. And if we just render, say, the first 120 frames per iteration till we get it right, we are down to maybe 10 seconds per iteration. So what I'm saying is that even an old laptop can handle a 250 million row data set with ease. Now we move to another example. This time we use the New York City yellow cab dataset, where all taxi trips in New York are stored since 2019. This dataset has 1.6 billion rows, and to show that it's easy to work with datasets of this size on a single computer, we've created an animation based on this data too. This dataset is of relatively high quality, but there are a lot of outliers and a few other issues. For example, if we create a heat map of the drop-off locations for one of the vendors, we get the plot to the top right here. We can see that it looks rather noisy. There are drop-offs all over the place, including the Hudson River. And even more worrying is that if we swap the longitude and the latitude coordinates, a mirror of New York City will manifest itself somewhere close to Antarctica. So some cleanup is required. The dataset contains a lot of information. Here we have created a minute-by-minute representation of the number of active taxi trips. We can, for example, zoom in on the January 2016 United States blizzard and study what happened then in great detail. The video, the example video that we will show, however, it shows the impact of the corona pandemic to the New York City taxi business. And I will start the video now. You can see 2 identical maps of New York City. To the left, we have 2019, and to the right, we have 2020. And the amount of taxi drop-offs are visualized in green. Now, as the number of confirmed cases of COVID-19 in New York City, here in blue, increases, we can see that the number of taxi trips in orange starts to decrease. This video is running at 60 frames per second, where each frame represents 1 hour New York time. And this video is also available on YouTube, and you can also find the source code that generates it on our GitHub page. Importing the 1.6 billion rows took less than 11 minutes. We don't need all this data for the video, but since importing is so fast, there is little point in importing less. Then we need to download some map tiles from OpenStreetMap, data about COVID cases, etc., and this takes 7 seconds. Most of this time is actually spent waiting in the OpenStreetMap API. The design iteration then is 12 seconds for this project, and added 26 seconds to that to encode the full video file before uploading it to YouTube. In addition to what has been already mentioned, ExAx has more features that are required or really helpful when running projects in production. In this talk, we've only got time to talk about one of them, the high performance access data. ExAx stores tabular data using something called a dataset. It's an efficient representation designed for high-speed parallel streaming access. The dataset is an extension of the job we mentioned. Datasets could be linked to each other vertically or horizontally to add more rows and columns in constant time. And datasets are strictly typed, but there are many types to choose from, including Python pickle, meaning that we can include almost anything in a dataset. Here is an illustration of how the data is stored. Imagine the taxi dataset with columns such as latitude, longitude, and timestamp. Each column is stored as separate files so that we do not need to go through all of the data in order to read just a single column. I would say reading one or a few columns is by far the most common case. Furthermore, each column is split into separate files or slices so that the different CPU cores in the machine can read one file each in parallel. Here is an example illustrating how efficient the dataset operations are. Imagine that we want to amend the model column in the Backblaze dataset. What we do then is that we read the model column one slice per CPU in parallel. We do the required modification on all the CPU cores, and then we write back the new column one file per CPU or slice. This is a perfectly parallel operation, and it requires very little memory since data is streamed through the program. And below here we can see an example what the code might look like. We read the model data from an iterator and we just write the modified data to a dataset writer. And this for loop is then run in parallel on all CPUs. And the modification we did was replacing a double space by a single space in this case. Note, however, that we never modify data. Instead, we create new columns, keeping the original ones for reference and reproducibility. Now, parallel processing works best if data can be partitioned into independent sets. Look at this example of a dataset with 3 slices. Our task is to compute how many fruits there are of each kind. Since, for example, apple exists in all 3 slices, we need to spend time and memory computing it, counting it in every slice. So we can only compute a partial result in each slice, and then we need to merge all these partial results to get our output. This is more or less how MapReduce works. It's both slow and memory intensive, and it can be done in a better way. The ExAx solution is to repartition the data based on a hash function. We move each fruit to the slice we get from applying a hash function to the fruit. In this example, we have apples and bananas hashing to the same slice, and they are marked with red. So all apples and bananas go to slice 0, kiwis and pears go to slice 1, and so on and so forth. Now, each fruit will then only exist in one slice, and we can count them independently. Processing is perfectly parallel, and there is no need to merge anything anymore. In addition, hash partitioning is a very fast operation and is run only once. The amortized cost approaches 0 as you reuse the result. And again, data is never modified. The hash partition data is stored in a new data set. So it's just another view of the same data. Yeah, so conclusion is that we can have faster development time, fewer mistakes, full transparency, and we can work with data sets of billions of rows in a few minutes on a single machine. And here I provide references to the blog, manual, and all the source code that was mentioned in this talk. Thank you.
Thank you so much. So we have a few questions. So from Alex, is this a Dask alternative? If so, how does it compare in design and performance?
Oh, that's a very good question. This runs on a single machine, so you don't need to bother to set up a cluster in order to run it. And you can run it on a laptop, or you can run it on a rack server with 100 CPUs if you like. So I would say it's kind of different.
Okay, we have another question from Maxim. How fast would your program run if it used pandas for importing dataset and pyarrow.parquet?
It's pretty different. We use a different way, a very efficient low-level way of storing things, and Parquet use another one. So they're not really compatible. Of course, you can transform from one to the other if you would like to. But we don't have any lock-in, so you can actually get the data out again into CSV file if you like. So I would say you don't need to use formats like Parquet to use this. You can just use CSV files.
Okay, great. So our time is over. If you have any more discussion that you would want to have with the speakers, please move it to Slack or GatherTown. Thank you so much to our speakers, Dr. Berkeman and Carl, for your talk and being part of the PyData Global 2021.
Thank you.